Thanks. So now the microphone is on, so the talk has officially started. Yeah. So I'm going to indeed talk about time change rigidity of unipotent flows. And so in my previous lecture, just sort of this is motivation, like I said, and I stand behind what I said, coming to the previous lectures is not needed to understand this talk, but in lecture 2 we discussed two dynamical systems. We discussed the flow, which are both connected to continuous fraction expansion. One of them is the flow, basically the action of the group this acting on SL2R modulo SL2Z. So that was one of them. And another was a map T, which took x to from 0, 1 to 0, 1, that took x to 1 over x minus integer part of 1 over x. So these are, so this is, one of them is an action of R, one of them is an action of Z. So actually, to say what I want to say in an accurate way, I'll take an invertible version of this last map. So it basically takes two numbers. One of them would be inside 0, 1, and one of them would be maybe bigger than 1, and it maps them to 1 over x. So first coordinate I perform t, and the second coordinate I am going to basically, sorry. So basically I'm erasing a digit in the continuous fraction expansion of x and moving it to the continuous fraction expansion of y. And now these two and somehow this AT are connected in an interesting way. As follows. So you have your three-dimensional system, and here you have some kind of two-dimensional cross-section, right? Because SL2R modulo SL2Z is a three-dimensional system, and here you have a two-dimensional cross-section. And when you go along AT, the first return map is going to be exactly, so this is x, this is going to be, this is a point x, this is going to be t hat of x. So this is a relation you could have between a flow, an action of R, and an invertible map, which is an action of Z. So that's an interesting connection. We are sort of going, this type of connection is going to play a key role in this talk. So definition, two Z actions I don't know, x mu t, x prime mu prime t prime are Kakutani equivalent if you could realize both. Both realized, as a first return map in the same flow, for a cross section in the same flow. So to get this invertible version of the Gauss map as a cross section in SL2R modulo SL2Z, you need to choose a cross section carefully. If you choose a different cross section, you would get a different map. And you could get two systems which are not isomorphic as abstract measure preserving systems, but still you could fit them together in the same flow.
Sorry, are we supposed to understand how the x and y variables fit in SL2 mod SL2?
No, it's somehow, it's just a motivation of getting two things which are, it's actually a bit tricky if you want to do it carefully. Essentially, you could think of morally, you have your fundamental domain for the hyperbolic plane modulo SL2Z. And morally, what you would, first approximation of what you do is you look at every time you cross this lower boundary. And each time you do that, it's that's sort of your cross section. It's two-dimensional because there's another dimension I'm not drawing of the direction, because SL2R modulo SL2Z is a unit tangent bundle, or perhaps double cover of the unit tangent bundle of the orbifold you get by gluing the fundamental domain. So that's morally the cross section. If you actually checked, you would see that it's not quite right. You need to do it a bit differently, but that's sort of morally how it sits. It's sort of a variation on this kind of thing. But I mean, that was sort of more of a motivation, because for me today, this kind of relationship between two systems, that you could fit them together in the same flow, is going to be center stage. And in fact, I'm not talking about diagonalizable action, I'm talking about unipotent flow. I'm trying to understand that. So the
measure, so on the cross section, there is no canonical measure. So measure is a part of data.
There is a reasonable way. So a cross section, by definition, basically means that there would be some there's some time that the action takes before it comes back. So it's true the cross section has zero measure, but if you thicken it in the direction of the action, it would have a positive measure. So at least you have a well-defined measure class on this cross section, and from this well-defined measure class, you could choose it so that the measure is actually invariant. And a dual definition to flows, I don't know, GT, X, mu GT. These are flows that preserve some measures, and X prime, U prime, GT prime are Kakutani equivalent. And I should say, all of this talking about inducing, etc., I'm only working, even if I'm not saying, I'm assuming that everything is ergodic, because basically I want to guarantee that I really am returning to the cross section, that it's not that I have two separate systems that somehow I'm not returning. So I'm assuming that everything is ergodic, so two ergodic flows. And for those who weren't in the previous talks, ergodic just means that you don't have invariant sets which are interesting. Any invariant set either has measure 0 or has full measure. So two ergodic flows are Kakutani equivalent if they have isomorphic sections So isomorphic dynamics and cross sections. So basically, I have two systems. I can find a cross section in one system, a cross section on the other system, so that the induced maps are isomorphic as measure preserving maps, which again, the flows can fail to be isomorphic. So it's somehow a coarse equivalence relation, then measure theoretic isomorphism. And to pass, so somehow, essentially, if one gives you given some dynamics, given a z action, to get a flow for which this is a cross section, there's essentially only one way. So you basically have you need some roof function. So z action may be x mu t. You need some roof function f from x to r plus in L1. And then what you do is that you're defining the map. So you define a new space in which you have a flow. X would be x times r, modulo an equivalence relation. The map is going to be g tau of xt would be x t plus tau. And the equivalence relation just says that the point x, fx, is equivalent to tx0. Okay, so basically, to get from a cross section to a flow, the abstract procedure that you do, ignoring topology of the space, etc., the abstract procedure that you do, you need to know how far you can go before you return to your cross section. There's another interpretation. So another interpretation of Kakutani equivalence of flows, another equivalent way to describe Kakutani equivalence. So I have these two flows. And on this flow, on one of them, doesn't matter which one, you give some speed limits. Okay, for every point, there's a speed limit. And the flow, instead of going at constant speed, it goes at the maximum speed allowed by this speed limit. So sometimes it goes, so initially it just went with speed 1, but now after the speed limit, sometimes it goes faster, sometimes it goes slower. Okay, so this is a time change. So the flow here is changed so that the speed limit given by this function v is observed. And the flow is ergodic, so somehow the average speed that you're going to get is going to be just the integral of v, and you want this average speed to be finite. You don't want, otherwise you sort of get in trouble. So v is some function in L1 of x. You need to modify the measure if you're time changing, so you're going through parts of your space faster, then you need to choose a different measure in the same measure class to get a measure preserving system. But two systems are Kakutani equivalent. So two systems are Kakutani equivalent if they can be time changed. One of them can be time changed to be isomorphic to another. So two systems our Kakutani equivalence if one can be changed, time changed, so that it is isomorphic as a measure preserving flow to the other. And if the average speed of the time change can be chosen to be 1, then we say that the systems are evenly Kakutani equivalent. Okay, it might be that two systems are equivalent up to time change, but the time change has to make you go faster or slower in a consistent way. Yeah.
So this is about equivalence of maths. So I guess locally it's the same as conjugacy, but the difference is that globally it can be rearranged into one another.
So you'd think this is a harmless operation, but it's not a harmless operation, as I'm going to demonstrate to you in a minute. It's actually so things can be Kakutani equivalent that would not seem to be similar. Right? You'd think this is a harmless operation. This is not a harmless operation. So there are certainly some things. It's not true that all dynamical. So when you define a new equivalence relation, the first thing you might worry about is maybe everything is equivalent to everything. That would not be so interesting. So certainly, so Kakutani equivalence preserves, it doesn't preserve entropy, but it preserves a class of zero entropy, finite entropy, and infinite entropy. So maybe the flow that this group gives on SL2R modulo SL2Z and the natural uniform Haar measure on the space, that would turn out to have entropy 1 in my normalization. Whereas if you look at the kind of flows that are going to be the stars of today's lecture, the unipotent flows, they have zero entropy. So this is not Kakutani equivalent to flow corresponding to the action of the group UT on same space. Now, define a system is said to be loosely Kronecker if it is Kakutani equivalence to the following simple system. So you have xy goes to x plus t, y plus alpha t, modulo 1. Okay, this is, I guess both coordinates are modulo 1. This is, let's call it gt. On r squared modulo z squared. Okay, so you have a straight line flow on a torus in an irrational angle. that's a nice system. Anything anything which is equivalent, Kakutani equivalent to this, is called loosely conical. And you might ask me what alpha, but so it turns out that all straight line flows of this type, if they're ergodic on tori, even a million dimensional, you can change alpha as long as it's an irrational number, are Kakutani equivalent. Are Kakutani equivalent, in particular, they are loosely conical. But many things you would not expect are also loosely conical. So
different alpha is not an invariant, not a Kakutani invariant.
Alpha is not a Kakutani invariant, absolutely not. Even though different alphas are, alpha is basically, you could read it from the spectrum of the corresponding unitary group, so it certainly is an invariant of the isomorphism class, measure isomorphism. But Ratner proved maybe I had the year, but sort of maybe give or take, maybe 1979, 78, sorry, give or take here, that's the answer, that unipotent flows, that the horocycle flow, which is how I would call this action of this one parameter group on SL2R modulo gamma, gamma lattice, are all loosely conical. These systems are mixing. The straight line flow on a torus is certainly not mixing, but there's still, you could change the time for the horocycle flow to get a straight line flow on a torus. Then there's 1 second, this is good, but 1 second. This is even though these systems are not isomorphic as measure preserving systems unless, so you have two systems, you have two lattices, unless for one lattice is going to be a conjugate of the other lattice. Right, so I haven't written the whole sentence here to save because I was lazy. I hope I didn't confuse anyone. I have two horocycle flows, the action of UT on SL2R modulo gamma, and then another one, the same UT on SL2R modulo gamma prime. They're both, like I said, they're both loosely conical, which in particular means that they are Kakutani equivalent to one another. But they cannot be isomorphic unless gamma is the conjugate of gamma prime. Yeah, there was a question.
So when you define the equivalence, you require that the speed limit is an L1. Would the situation change dramatically if you needed it to be smooth?
Yes and no. So along the direction of the flow, you could get everything to be smooth, but if you require the time change to be smooth in other ways, then actually it becomes a strictly more restrictive notion.
My guesses would be that none of those results would hold if you instead of if you required it to be smooth. Right?
This is your guess, and this is a theorem of Ratner. It's not, it's correct. It's not a trivial thing to prove, but it is correct.
Is the speed limit something you can write down in this case, or something that just
it's yeah, it's more. I mean, you could understand it in fairly concrete terms, but the way you show it is that you sort of give there's a condition about a dynamical system which implies it's loosely chronicle. You can check this condition, and then you could work through this definition. Why this implies that to maybe write some kind of speed limit, but it's not a natural thing that you would write. In particular, because anything natural that you would write would probably end up to be smooth.
Does it use symbolic dynamics, like writing it digit by digit, roughly speaking, somewhere this way?
Use is a strong word. I mean, you sort of.
So can I ask about the if you have a two-dimensional smooth flow, then you have this concurrent Bendixson description of what can happen. And so would be invariance, like you have cycles, and suppose you take area between cycles, that would be a Kokoutani invariant?
Unlikely. I mean, remember, everything here is not continuous, just measurable. So you change things in the fact that it's sort of measurable is a big deal.
So this is only matters if there are positive measure of points which cycle.
But here sort of, so this theorem of Ratner, once you know the criterion, is not very hard. But what surprised people is that in Ratner, a few years later, maybe 1980, proved something very surprising. Proved that if you take a product of two of these systems, that if you take SL2R mod gamma times SL2R modulo maybe the same gamma, maybe different gamma, doesn't matter. So you take two of these systems and you act on it by applying UT in each component is not loosely chronicle. So the people who were studying this equivalence class at this time, I don't know, Feldman, Ornstein, Benji Weiss, they knew how to construct exotic examples of loosely chronicle systems whose product with themselves is not loosely chronicle. But Ratner then said, I mean, this is not, you don't need to do something very exotic. You take one of the most beautiful, simple examples of something which is loosely chronicle. Its product with itself is not loosely chronicle. And that's sort of a much harder paper in my mind. That's actually what got Ratner into unipotent flows and eventually led to these wonderful theorems I described in my first lecture.
So definition of loosely chronicle is two-dimensional torus, but actually a system in 5 dimension can also be equivalent to a 2-dimension because things are not.
Yeah, so a 10-dimensional torus is also loosely equivalent to a 2-dimensional torus. It's not a dimension invariant. It's not. It's sort of. It's a subtle equivalence relation, and it's quite hard to show that something is not an equivalence relation. How would you show that something is not an equivalence relation? So what she did this by defining an invariant. Ratner did this by defining some entropy-like invariant, but of course all of these are zero entropy. An invariant under Kakutan equivalence that distinguishes is zero if and only if the system is loosely chronicle. Loosely chronicle and is non-zero. In fact, she essentially calculated it for SL2R modulo gamma times SL2R modulo gamma prime. She actually calculated it, or almost calculated it in her paper. And what she also showed, using this invariant, she also showed that K products of horocycle flows are not Kakutani equivalent to L products if L is not equal to K.
These products Kakutani equivalent to each other?
That is exactly the question. So this is a question that, so her invariant, Ratner's invariant, does not distinguish between let's say the UT action on SL2R times SL2R mod gamma, whatever gamma is. So maybe gamma is a product of two lattices, maybe gamma is an irreducible lattice. Ratner's invariant gives the same value, whatever, 1, 2, to all of these systems. And then this was a question of Ratner's that Ratner asked, in particular in her ICM address from 94, probably was around also earlier. Are these Kakutani equivalents? The invariant is the same. If you look at just one factor, like I said, if you have only one factor, if you just have SL2R modulo gamma, because they're loosely Kronecker, for all gammas, you have systems which are Kakutani equivalent to one another. Maybe this Kakutani invariant is the complete invariant.
So the system in the definition, you just have a torus. If you take a product of that with itself, you were saying that is
yeah.
loosely Kronecker.
I'm with Hades, as long as it's, yeah. No, it's not going to be ergodic, so just take maybe, but with different alphas, it's not going to be, yeah, I'm only talking about ergodic systems. If you take a product with itself, the difference is going to be the, yeah, absolutely. So there, as far as I know, the problem has, so this was basically asked maybe in 90, it was asked before, but sort of the written record that I know of is from 90-something, 94 probably, Ratner gave her ICM address. Seems, I don't think there was any kind of progress on this until there was a paper by Kanigovsky, Vinhage, and Darren Way, so they calculated Ratner's invariant for any unipotent action, any action of one unipotent one parameter group on a quotient G mod gamma, G being a linear algebraic group over R, or in fact connected component. So a linear algebraic group over R maybe the solution of your polynomial equations have two components, or connected components of a linear algebraic group over R, and gamma a lattice. I think they were assuming G also semi-simple, which is also the generality that I'm going to discuss in today's talk. So we are looking at a group like, and really I think SL2R times SL2R is maybe the only group you need to think about for this lecture. But in general, you could look at a group of matrices satisfying some equations that is semi-simple, whatever I'm not going to define that, but also maybe SLNR or product of SLNR and another SLNR or something, SLNC, various examples.
So this invariant is a real number or integer or what?
It's a real number, which turns out to be an integer for these examples. And the one parameter unipotent group, right? So I talked about group of matrices, so it's something that looks like xt times some nilpotent element, n is in the Lie group of Lie algebra of G. And in particular, what they showed is that ut on G mod gamma is loosely Kronecker if and only if I can write the Lie algebra of G as some SL2R direct product with something, and my element n is inside this SL2. This is a representation as a Lie algebra, so I'm sort of a direct sum of two things which commute with one another, and my element is inside the SL2. So for instance, also, basically there's no examples beyond what Ratner proved. There's one kind of example. So for instance, if you look at the UT ID, e.g., to make it clear what I mean, if you look at the action of UT and the identity on SL2R times SL2R modulo gamma, gamma irreducible, remember I'm only looking at the case of ergodic flows. So if I took here SL2R times SL2R modulo a product of lattices, then this is not going to be ergodic, so it's going to be thrown out to begin with. But if I'm looking modulo an irreducible lattice, this action is going to be ergodic, and it is also loosely Kronecker. And that's the only way to have loosely Kronecker things, and all of them are equivalent to one another because that's the definition of loosely Kronecker. And what I want to present today, in the time that I have, is a theorem, joint work with Darren Way, which answers Ratner's question in, I think, a strong way. So here is the theorem, or maybe setup to begin with. So let's set up, like we said. So we have GI, I from 1, 2, semi-simple, linear algebraic group over R, and I'm not taking, I'm just taking the connected component of the identity, finitely many connected components possibly. Gamma I inside GI is a lattice, and then UI, UIT inside GI are one parameter unipotent. And then the theorem says, and of course I'm asking that you acting ergodically on Gi modulo gamma, and we know exactly what this happens. In particular, if gamma is an irreducible lattice, this is automatic. And now, okay, so this is a setup. So now I can give the theorem, which is, like I said, don't work with Darren Way. If UIT Gi mod gamma, and of course the uniform measure on the space are Kakutani equivalent, then either one option is that both are loosely conical. We know exactly when this happens. Or the second option, that they are in fact isomorphic. Measure preserving systems. These very strong measure classification theorems of Ratner, or in fact earlier results that she had, completely classify when these kind of systems can be isomorphic to one another. There's basically no surprises. Basically, G1 needs to be equal to G2, gamma 1 needs to be equal to gamma 2, maybe up to a conjugation. UIT, U1 must be equal to U1, and basically there are no, the isomorphism, I'm saying here isomorphic as measure preserving systems, but it sort of basically means that there's an obvious continuous algebraic map that you just have to be careful to say it, because maybe you have some double cover of G, and it's sort of eaten by some element of gamma. But basically G, the groups have to be the same, the lattices have to be the same, the unipotent group has to be the same. That's the theorem. And so basically this means that G1 is equal to G2. Maybe you need to make some kind of very minor assumption. Gamma 1 is a conjugate of gamma 2. Yeah, that's why, I mean, finite covering, but of course, I mean, I have Kakutani equivalence at the end of the day is talks about isomorphism. So it's not that you can have, so it's not that, in particular, if you look here at SL2R modulo some lattice, and not SL2R, that's not a good, but SL3R modulo a lattice, and SL3R modulo a congruence lattice, these are not Kakutani equivalent.
No, but I mean, if you take PSL3 modulo lattice, and then...
Yeah, that's what I said. You have to be, that's why I wrote it this way, because I didn't want to get into this kind of question that, I mean, yeah, exactly, I didn't want to have to say it carefully that I'm not taking finite covers and compensating for that by taking a slightly larger lattice or something like that. So this is a theorem. Maybe try to put the main steps of the proof in the quarter of an hour that I have. So there's a notion which is sort of basic when you study Kakutani equivalence. So let's start just with definition, which is certainly not ours. It sort of goes back to the pioneering work of Feldman and other people. UT orbit of 2 points, x and x prime in some space x are delta epsilon t matchable if there is a subset A in minus tt, A is bigger than 1 minus epsilon times 2t or something, so a big subset of this interval for minus t to t, and a monotone, absolutely continuous, whatever map H from minus t to R, or with, or maybe to minus tt. Derivative minus 1 is less than epsilon on A. So essentially, derivative is very close to 1. Maybe this was supposed to be H. Such that for t in A, the distance between ut of x and uht of x prime is less than delta. Okay, so this is exactly saying that you could, this is some kind of statement on an orbit level that you could time change in a gentle way one orbit to match the other orbits. That's obviously related to the notion of Kakutani equivalence, or time change to be more precise. And now there's a basic lemma that, so if we were working on G, so if I had 2 points are inside some group G, which, I mean, it would either be G1 or G2. I'm sort of going to do this kind of game in either of these two groups. So if I have 2 points in a group G, then it's easy to say when G and G prime are somehow, that's not where the dynamics actually occurs, but you could still, the definition still makes sense. Matchable if and only if G is equal to some eta G prime, and if you look at eta is a small element, so I can look at its logarithm, it's some element of the Lie algebra, you could write it, so write it as some kind of, or even better, I'm not going to take G, I'm going to apply, so in semi-simple groups, every unipotent element is an, so let me say it this way. So let me say one thing before. So I had here ut comes from some element of the Lie algebra, and by Jacobson-Morozov, so I would have to erase this. You can find two, I don't know, two other elements. Let's call it H or A, and let's call it V, such that N, A, and V span a representation of SL2 with the right identity. So actually our SL2 triplet. In particular, if AT is exp T times A, then I'm going to have that AT US A minus T is going to be U e to the minus e to the plus T S. Okay, so that somehow I have this element, diagonal element, that normalizes my group and sort of contracts it, and it's not any element will do, but an element which actually sits together with my unipotent group in an SL2. And then these two elements have to be related by the fact that if I apply a to the minus t for t, or a to the minus log t of g, and I write it as eta a to the minus log t of g prime, then g and g prime are g and g prime so now write the Lie algebra of G as the Lie algebra of this SL2, and then some union of representation, irreducible representation. These are irreducible, let's say, Lie representations of the SL2, or irreducible representations of the lift of this group, irreducible SL2 representations. And then and then you could write this log of eta, write log of eta as some component, I don't know, eta in H, and some component in each one of these representations. So basically, eta of H would be smaller than some delta prime, which would depend on delta so if 2 points are so if G and G prime are epsilon delta t matchable, then after you do all of this procedure, basically this eta H would be less than something small, which depends on the epsilon and delta, but the other components are going to be even smaller. They would be smaller than some delta prime times t to the minus the dimension of vi minus 1 over 2, something like that. Okay, so somehow, it's not so important. You could calculate it somehow, kind of calculation, Lie algebra, if you have 2 points when they are matchable. That's sort of easy. The VIs can be one-dimensional. In this case, this number is 0. That's absolutely correct. That doesn't happen in the case of SL2 times SL2 that is sort of my motivating example, but it certainly happens, and it's a complication in the argument. But the basic lemma, which is so the basic lemma, which is based on ideas of Ratner, refined by Kanigovsky, Vinhage, and Weil, and then further made more quantitative by us. But the basic lemma says that if 2 points, which is the coset of some g, and x prime, which is the coset of some g prime, are epsilon delta t matchable, then they have lifts that are lifts to G that are matchable. So basically, and this is basic lemma, if this is matchable, and if the system, so if we are not in the loosely Bernoulli case, loosely Bernoulli, loosely Kronecker, this is not quite a mistake, because some people use, instead of loosely Kronecker, they say loosely Bernoulli of entropy 0, but loosely Kronecker seems to me a better name. If not loosely Kronecker, probably it's also true in the loosely Kronecker case in a vacuous sense, then you could understand being matchable in G mod gamma, even though this lattice gamma sort of allows you to match things. Things are near each other in G mod gamma that are not near in G, obviously, because you're quotienting by gamma. So that's sort of one ingredient, an important ingredient. Then step 2 is to say, or let's say step 2 and 3 together, on a large set, maybe after, so suppose now you have a Kakutani equivalence. So suppose you have a Kakutani equivalence. Suppose psi is Kakutani equivalence between the GI modulo gamma I. Now Kakutani equivalence, more or less by its definition, by time change, they match epsilon delta t matchable trajectories to, okay, epsilon prime, delta prime, t matchable trajectories. It preserves up to the exact value of the epsilon and delta. It preserves this relation of being matchable. So if you have pairs in G1 mod gamma 1 that are matchable because you understand their relation to each other, because they're sort of in this kind of Kakutani ball, their image, and I should say this, there's a set that sort of are epsilon on a set of large measure. It's not true everywhere, on a set of large measure, of measure bigger than 0.99, okay? It's not true for every point x and x prime, only on a set of measure bigger than 0.99, you have this relation. Now, so this immediately, basic lemma immediately says that a pair of, that on a set of large measure, 2 points which have some geometric configuration, one with respect to the other, will be mapped to points which have a similar geometric configuration on the other side. But now, what you get, you could use that to show that if you take if you apply an element of the diagonal group to a point and you apply this Kakutani equivalent, so at least if t is small, because of this commutation relationship between u and t, if t is very small, ATX and X are epsilon delta matchable for arbitrarily long time. So this implies a very strong statement about the image, and here exactly this fact that you might have one-dimensional representation sort of becomes a complication, but eventually what you could show, maybe not on the original psi, after modifying it by an element of the centralizer view, you get that this would be so this is this lives in G1 mod gamma 1. After psi, you live in G2 mod gamma 2. So basically, if you apply an element of the diagonal group before you apply psi, it's the same as if you apply an element of the diagonal group after you apply psi, but there is some shift in the flow direction that you don't have any control. That's sort of steps 2 and 3. And then the hardest step, which unfortunately I don't have time to describe, but the hardest step so then step 4, which is the hardest, at least for us was the hardest, is to show that in a certain sense, so in particular, maybe let's call the function, so maybe let's call u1x phi of x or something, or is u of phi of x, let's be more precise, is u of some f of x. Okay, and the only thing I know about f of x is it's a measurable function, so it's almost everywhere finite, but it's not L1, not anything. It's just almost everywhere finite. So if I'm looking at unx from this, so it's basically going to be, so this is, I'm applying this kind of thing n times. It's, if you sort of work out what it means, it would be something like f of x plus, hopefully I got it right and it's not the other way around, but I think it's f of x plus e to the minus 1 f of at of a1x plus e to the minus n plus 1 f of anx. So it's some kind of, so if you knew, for instance, that f was bounded, this would be a convergent sequence. But of course, the only thing you know about f is that it's a measurable function, so you don't have any kind of control over this kind of average. But what you, so the hard part is to show that you could, that actually, in fact, you need to show that if you take a2 minus n of psi of a1 n of x, right? So you sort of start with the point, you apply a big element of the diagonal group that sort of expands your unipotent drastically, or maybe the opposite direction. Now I'm sort of confused. Maybe you do it the other direction. I think I did it correctly. So you do this and then you do this. So you apply a big element here, you apply psi, you apply something to compensate. So this is, for any n, this is a shift of x in the unipotent direction. You want to show this converges in the appropriate sense to some limiting object, psi tilde of x, with psi tilde of x inside the u orbit of psi of x. Okay, so you have this kind of shift that is a priori just a measurable function, and you somehow have to convince it to converge. Once you have this limiting object, it's easy to see, is going to be, in fact, once you prove this, the limiting object is the desired isomorphism between the systems. So it's not just that I tell you which quotients are isomorphic, which quotients are loosely Kronecker. I'm actually telling you that if you have this kind of Kakutani equivalence that comes from a time change, it has to be somehow a very simple form that you sort of just, in an appropriate sense, it's sort of just you move by a co-cycle. I mean, sort of it's kind of a trivial, only trivial time changes can give you an isomorphism between unipotent flows. So, okay, let's see if there's something I want to say to conclude. I need to find the end of my, yeah, so somehow in my first talk we talked about rigidity properties of unipotent flows, and each orbit was equidistributed in a nice homogeneous subspace, and these results in particular imply the isomorphism rigidity, that sort of a measurable isomorphism is actually a much nicer isomorphism, but there's sort of a dichotomy if you're talking about time change, that if we are in the loosely Kronecker case, so quotients of SL2 essentially, there's no rigidity, but once we go beyond that, the rigidity even survives this kind of rather aggressive time change. And the key of the proof is via this kind of renormalization procedure that brings you from an arbitrary Kakutani equivalence to a isomorphism. This strategy of this kind of renormalization was actually used by Ratner in her work that I alluded to earlier, showing that if you have a smooth time change, you cannot get non-isomorphic horocycle flows to become isomorphic. But because you don't have any kind of smoothness, showing that this limit exists becomes harder. Okay, thank you.
So are there any questions?
So just telepathically sending them to you, but
Well, I will ask it no problem. I have some questions right now. So you consider this smooth flows, and the lowest example where you had this rigidity was dimension 6, right? SL2R cross SL2R. So what is the lowest dimension of flows? I suppose at least 3, right? Because you want a harmonic flow, for which you have non-Kronecker, loosely Kronecker flow. Does it exist in dimension 3 maybe or 4?
In some sense, it's not you could create for smooth flows, okay. I mean, but you could make flows which are basically in a one-dimensional space, which is sort of, you have the flow and then the cross-section is a Cantor set, which would not be loosely Kronecker. That's what I was, in general, it's a great mystery what kind of dynamical systems you could realize in a smooth system. One of the most interesting questions, oldest questions in ergodic theory is, what are the restrictions? If I tell you that some flow or some, let's say even a map, you have some a map, a measurable z action. Can it be realized as a smooth measure on a smooth manifold and you have a C2 map on it? So there's one restriction I know. The entropy has to be finite. I'm not sure, I don't think there's any other restriction known. So I mean, this kind of questions, what can you realize as a smooth dynamics? These are quite hard, and I'm not the expert on them, but
so
they would be.
If examples exist in lower dimensions,
I don't know.
or maybe on compact manifolds, because these are not compact.
These are often compact. Sometimes they are compact. They're often compact. That's not. I think Ratner proved her theorem about products in the compact case. I'm not sure. I mean, it doesn't really make so much difference except a minor complication. But I mean, these examples are often compact. That's not the issue. Compact, not compact in this particular question.
But its dimension is not so clear yet. So are there other examples than these for which are not Kronecker? I mean, other known examples for which it is proved that they are not loosely Kronecker?
Yeah, like I said, I mean, even so, this was basically the pioneering work of Feldman and Weiss and Ornstein. They sort of understood what it means. And one thing I should have said, right? Loosely Kronecker means, in particular, they have zero entropies. Of course, if you take a two-dimensional toral automorphism and you somehow you do some kind of suspension construction on it, that's a three-dimensional system which has positive entropy, so it's not going to be loosely Kronecker. but that's sort of cheating. I mean, you might ask about zero entropy systems, and sort of anyway, that sort of might be a harder question.
This is a smooth system, or
You could make it smooth, right? I mean, you could sort of somehow. I mean, this is a nice manifold. You take a torus, and you glue it with a. You could make it even a hyperbolic manifold. I mean, this is exactly the kind of thing that Thurston likes, etc. That sort of.
So this answers my question that yes, in 3 dimensions you can construct, but it's not very interesting. In the
Yeah.
sense that it has this coarse invariant, which is empirically not equal.
Yeah.
Other questions?
Yes,
Semyon.
just to clarify, so today, unlike the previous 2 lectures, you didn't need anything to be arithmetic.
No, no, nothing arithmetic here. No.
Other questions? Okay, let us think.